Good morning, everyone. I'm so delighted to meet the next generation of heavy APS, Oak Ridge, and other laboratories users. So I will be talking about high pressure, and you have heard about it here and there. You have seen beamlines that run high pressure. So I'm in this hour, I will like to try and give, put these pieces together, organize them. Of course, the topic is huge, is very broad, so my presentation cannot be very deep in most of these topics, except for maybe the final example, which is my work, which is not the most important in the world, but it allows me to go in some details to tell a more detailed story. So I'll talk about high pressure in the universe, different kind of high pressure research, a very basic overview of high pressure devices, how you generate high pressure, the relationship between high pressure and these sources that you have visited and you're interested to use. Some highlights that just tells very recent highlights just to tell the story or some insight on how high pressure is actually breaking new grounds every year. It's very, very dynamic, very fundamental technique. Then I would really also like to talk about, I'm going to talk about and deliver to you the message of the reality of these non-ambient experiments, so environmental studies, because your measurements in high pressure science and so many other kind of experiments that you are going to design is going to be your own, will give you data that most likely are not going to be the most beautiful data that you have exercised on. And you need to be able to, on one hand, have the deep understanding to handle these not so great data, to interpret properly as far as they can take you, to understand where you have to stop, and then to keep improving. So high pressure is one of the most dynamic sciences. So maybe what yesterday was an acceptable standards for the kind of data you could collect at certain pressure and temperature, you will be the one that push that limit and get better data. And that's why I will talk about my experience, because that's what I did really, pushing diffraction to a different level for certain materials. So pressure is a fundamental intrinsic variable that changes immensely in the universe. Of course, from very low pressure of intergalactic voids, but extremely low pressure in the APS storage ring, I learned. Here I will be talking about high pressure, and there aren't very distinct limits in the community because there's so many communities. So for some communities, half a GPa might be already high pressure. This is still not the high blood pressure, but it's, for some people, for some careers, they are limited to quite low pressures. But already 5 GPa is enough to stabilize diamonds with respect to graphite, and that's where we start really the work of high pressure, the way most of the high pressure community think about. By 10 GPa, all your very light gases that in your mind are it's extremely volatile, become solid. The center of the Earth is 360 GPa, and these are conditions that we can achieve almost routinely. It's very tough, but 360 GPa can be achieved quite routinely. 500 GPa, this is one of these very recent groundbreaking discovery, and something that the high pressure community have been chasing for decades, is metallization of hydrogen. So it's not just a solid it goes through different phase transitions. It becomes non-transparent and then reflective at almost 500 GPa. Greater pressure, of course, inside large planets, inside the sun, and larger bodies. So, of course, high pressure and geoscience being high pressure found in if we scratch the surface of our planet, is where we find high pressure. So the geoscience community has been involved heavily in high pressure for the longest time. And that's because our environment, our atmosphere, the oceans, the crust where we live in, the materials we find around are related to high pressure processes. We breathe air that came out of volcanoes, outgassing of the planets for the most part. So there is this, we want to really understand how that came about, how it happened, and we also want to understand deep earth processes that relate to what happens today, namely volcanoes and earthquakes, just to mention the most obvious. Some of them, like Hawaii, the roots of all volcanism is extremely deep inside the earth. So you want to understand what are the conditions of what materials you might have in there, chemistry, composition, mechanical properties as well. Of course, you have impact, and during impacts you generate very high pressures. Well, of course, pressures in the whole range, depending on the size of the impact, and those are also extremely important in the formation of planets in general, and of course in events such as the extinction of dinosaurs and so forth. And if you want to understand big planets out there and stars, etc., of course, most of their material is at extremely high pressure. So you can take ambient pressure as for us is an exception, just a particular one. In the previous talk, national security was also mentioned. I just reported here a statement from the NNSA website. Extreme conditions of high pressure and temperatures are relevant for national security, so they are a big part of the NNSA mission. And what that means is also that NNSA supports not only their laboratories and their research that they conduct, and that's still good to know because it could be job opportunities for you, but it also supports these impressive laboratories where all kind of science is being conducted. So here I report two slides of NIF and Livermore Z-pinch machines. These are extremely large scale facilities, right? Very few universities, well, I don't think any university can have something of this scale, and they run user programs as well. So there's science, job opportunities in science being conducted. And of course, my center is also funded by these NNSA for this purpose. And we have material science. Of course, I named diamond. Diamond is a material we use to drill and for applications all the time. So as pressure is an extremely powerful tool to change matter in any possible ways, so we routinely go to pressures that are high enough to add to the material the same amount of energy of a bond and more. So of course you're changing it so deeply, so profoundly. So you can synthesize materials that you cannot possibly synthesize without high pressure. You can induce and change all its properties dramatically. The areas where most research is being done is super hard materials. Of course, there's diamonds, boron nitride, there's nitrides of transition metals, for instance. superconductivity and magnetic properties, high energy density and hydrogen storage, also a very active area of research, and nuclear waste. There's also, I don't know if many of you are from the biological side, but there's application and studies at high pressure for biology and medicine as well. This is really something I don't know very much about, but you can still use high pressure to synthesize polymorphs of pharmaceutical compounds. They can be delivered at different stages in a digestion process, for instance. And very important to also mention is that just like diamond, the high pressure community might find out this material, and then it is often possible, just like in case of diamond, to make it without the use of high pressure. You can use chemical or other techniques to try and find the same properties on the same material, other materials, and make it so that you can have a large-scale production of it. There's food preservation and bacteria being studied under pressure. I don't think they like it, but it's going on. Of course, all these applications go back to your fundamental physics and chemistry that you need to grasp in order to understand all these applications. And it's, of course, extremely exciting. And it's by studying materials under high pressure, you can really deepen your fundamental understanding. You are adding so much energy to the system. You're fundamentally altering the way you think about elements, right? The way you think about hydrogen, the high pressure community, don't think about hydrogen as your average person does. So what are we studying in those application and in fundamental physics and chemistry? I'll show you in the example that still elements are being deeply investigated and have so many secrets. So we are far from knowing everything about high pressure. So we study phase diagram. We want to understand how pressure changes. Of course, materials go even gases through liquid and then become solids, and then you have solid to solid transition. So you want to study the crystal structure via diffraction for the most part, Raman spectroscopy of all these phases. You want to study the melting lines and the melting of materials. You just want to study the melt. There are different phases in many materials within as a function of pressure while you melt in the melt. You want to study deformation, and in the previous talk already introduced this problem. We want to study how materials respond to pressure, both from the atomic scale. So we are looking at the crystal structure. We are looking, well, if you apply hydrostatic pressure, what changes, what bond, how do they change, and why. We want to have a general understanding of the compressibility and how a crystal structure take that change in volume that you are imposing. And we want to understand the bulk response in the deformation, and we want to understand both in hydrostatic conditions and non-hydrostatic conditions. We want to understand crystals in a quasi-hydrostatic medium in ideal conditions, and we want to understand something like a piece of rock under very high pressure and temperatures, like in your subduction zone. You want to understand what happened to the assembly, not just the phase in ideal state, because that assembly is what affects properties, is what drives your earthquakes and such. Electrical and magnetic properties, I'll show an example about it. You are forcing bonds to come and material to come apart. You're altering orbitals, you're altering the electronic properties so much. So these are changed dramatically. And so we want to understand what happened, what is the chemistry of high pressure. This is completely exotic, and we just begin to understand it, mostly because it's very difficult to do these experiments. So how do we generate high pressure? I believe you guys have toured beam lines, and you've probably have seen something. I've seen some other lectures showing some of these devices. Devices are divided in static and dynamic. Static, you can keep it there for a very long time. Dynamics is a shock. So static high pressure devices are, is this one? Divided in these three groups mainly. The diamond anvil cell is by far the most common. It can reach pressures that are really high, and it's a handheld device. It's a very small sample size. I will go through later. Then you have static larger presses, and you have these dynamics. You see that each device has its own pressure and temperature range. And of course, these limits are far from static. They are broken all the time. This is from last year's book, and it's already outdated. Of course, also the dynamic range, this plot is just cut out, but the dynamic range can go much higher than this. So the diamond anvil cell is a device that you can hold in your hands. It allows you to push against each other the two diamonds, and you put a sample in between these two diamonds, in between the tips of the two diamonds. You make a sample chamber, usually using a metal foil. You make an indentation, you drill a teeny tiny hole in there, and you create your little sample chamber. So this device, which is typically hardened steel, very well machined, allowed to apply this axial compression, allowed to align the diamonds, because if you don't have everything perfect, of course, even the hardest of materials, diamond will shatter immediately. But if you have a very good device, you can really squeeze them together. In this sketch of the sample chamber, you actually show that curvature, because even at pressure that for ours are not particularly high, you are bending elastically diamonds like that, and your sample chamber remains confined within this small volume. The volume of a sample here ranges from few microns to maybe 200-300 microns, but say 10 microns is your most common average size. It can go to 1,000 GPa. You can put in a cryostat and take it to few Kelvin. You can heat the whole thing. Of course, everything is difficult, so your equipment will respond to heat, and if it deforms too much, you might break diamonds like that. But you can heat delivering lasers through these diamonds and go to several thousand Kelvin. I don't know what's the highest. The record is certainly on the order of 6,000-7,000 Kelvin or more. Several techniques that you have learned can only be applied to diamond anvil cell studies as of today. It will be obvious from the picture of the other devices. These are two recent breakthrough in the diamond anvil cell design. So in high pressure, you have these advances that are from generating high pressure, from probing, so your techniques for probing samples, not only the science that you do. So this group in Germany used a 20-micron spheres of nano-sized diamond that it was cut in a FIB, in a TEM machine, and as a secondary stage anvil. So in between two diamonds tip, which is already crazy if you think about, they managed to put to a semi-sphere and put the sample there in between, and they claim to have gone to 1,000 GPa. There's also other groups challenging actually these results, and it's going to be just fun to see how that developed. And here in this lab, they actually did a very impressive development that will be extremely crucial for neutron applications, neutron experiments at high pressure. They developed very large diamonds and very large loads that you can apply to diamonds. It's very difficult. You need to design these materials for their strengths, for their shape, in order to sustain these kind of pressures and without breaking right away. And so the plot shows how those red spots shows how much higher a volume they could obtain for a given pressure. So they bringing up the volume size opens up the possibility for more neutron experiments. They managed to study deuterated water to almost 100 GPa, which was unimaginable for me just a few years ago. Multi-anvil presses are almost size of a small room, so they are extremely large devices. Hence, some of your forward scattering techniques are not very friendly with this device. You cannot bring it in any beamline and do whatever you want, or cool the entire thing. That's not easy to do. So they usually have several stages and anvils within the machine. You can apply extremely large loads to them, and the whole reason you want these sort of machines is that you can have very much larger samples, and with larger samples comes a whole kind of different type of studies that you can do, especially these multi-grain or mesoscale studies. It's very important to material science. Anytime you can recover phase, this machine will give you a sample that you can do all these other kind of experiments at ambient condition in the recovered sample, for instance. Some of these machines you can actually drive these external pistons in the different ways, and you can apply on an actual load and so see how a material responds to a confining pressure and an actual pressure being changed. The Paris-Enneberg cell is something somewhat in between. It's most popular for neutron science. It's of this size roughly. So it allows, without the size of a multi-anvil large volume press, to achieve quite large sample volumes. Indeed, it can also be cooled at very least to liquid nitrogen temperatures, but I also think below. It has tungsten carbide anvils for the most part, but they are also starting using sintered nano crystalline diamonds as well. And of course, shock compression is almost a different community. The dynamic, of course, we do all high pressure. Still, shock compression has a whole different technology, a whole different type of probing the sample under extreme conditions. So the very amazing news is that the dynamic compression sector, 35 at DCS, started just a couple of years ago, and is up and running. It has hutches with these devices. Shock compression devices are usually basically guns which are gas gun or powder guns, or you're shooting projectiles on a sample, or laser ablation ones. These are pictures from the APS. There are some, of course, around the world. By the way, I'm showing mostly APS US devices, but of course there's a larger worldwide high pressure community. And so those at these laboratories are not the largest in the world. I showed you a picture from NNSA facilities. But they can reach extremely high pressure, but the sample, of course, has a very short life. So usually also the sample will always go heat because of the energy, being applied to in this extremely fast rate. You have strain rates that are extremely high, and you have a shock wave going through. So given these conditions that I summarized, it's quite obvious why high pressure community loves these laboratories. So you have a very small sample, or a sample in a bulk device, and you can see that sample only through narrow semi-transparent windows, and the sample might be very short-lived. Samples can also be or in general, they tend to be extremely complex, because if you picture things, you're smashing something, it's not going to be your ideal beautiful sample. And if you start heating different techniques, you start immediately having high and low pressure phases, part of samples reacted and unreacted. So of course you want high flux just to be able to collect a decent signal from a small sample, or to collect a signal in short time of a shock compression. You want a beam of the right size, so it goes through the window and gets to the sample, and it doesn't illuminate everything, all the device, because of course everything will scatter your radiation. So you want to minimize the parasitic scattering and optimize your sample to parasitic scattering ratio. You want a tunable energy if your technique allows you to just select the energy. So you can go, you can select your devices, your materials to go through and optimize again, minimize absorption and scattering of this material and optimize your signal. So of course, high pressure is very thirsty of brilliance. All right. Here is an outline I circled, the APS beam lines that have some high pressure science being performed at. Two sectors, sector 16, which my group is member of and I know the best, has 100% is fully dedicated to high pressure, static or quasi-static exclusively, and the dynamic compression sector. So HPCAT has 4 beam lines, several techniques, diffraction spectroscopies, several sample environment techniques. So you can go high temperature, low temperature, you name it. And the dynamic compression sector will be dedicated to shock compression only. It's not open to users as far as I know, but it will be soon. Then GC-CARS sector 13 is also heavily invested in high pressure science. It's more than 50% for sure. They also run a whole bunch of techniques and a whole bunch of high pressure devices available. Sector 3 and 4, they are almost on 50%, 40% roughly, just a figure of merit. High pressure, they do mostly properties, so nuclear scattering and extreme magnetic dichroism, absorption spectroscopy. So they're looking at the properties of materials for geoscience application, materials and physics for the most part. The yellow circles show other beam lines. They have around some high pressure. I don't know what's the percentage really, but it gives you an idea of the broad range of technique. The weight of high pressure in these impressive laboratories. So it is a popular science in these laboratories. Here you have one beamline. If you look at the ratio, we're roughly getting comparable to APS, right? So one beamline is fully dedicated, is a diffraction beamline to high pressure. And that's the beamline that developed that new diamond anvil cell. But high pressure experiments have been performed in these other highlighted in yellow beamlines. So I'll show you now a few highlights, very recent highlights, very groundbreaking results in high pressure science. So a couple of years ago, this group from Germany finally reached this superconductivity. High pressure has been predicted for a very long time, and this group managed to actually obtain measurements of superconductivity, very high temperature, around 200 Kelvin at roughly 200 GPa. This is extremely difficult experiment. They literally have in this diamond, in between the tips of the diamond, they literally have leads to measure conductivity through the sample. The sample is also going through its hydrogen sulfide, so light scatter. It goes through transition. So as of today, it's not even clear what is the stoichiometry, what is a compound that is responsible for this superconductivity. Another experiment that the same group did later is a nuclear forward scattering experiment that is very clever, interesting. The way it's conducted, the sample subjected to these high pressure and low temperature. So you have to imagine that 200 GPa in a cryostat and a magnetic field, and they change temperature of these samples, and they observe that and they put actually a tin foil, a very small tin foil, in and surrounded by the sample that becomes superconductive, and they show that the sample become basically shielded by from the external magnetic field when it becomes superconductive. By the way, the same group already in these two different experiments find several tens of degree Kelvin differences, which they claim might be due to bulk or full or non-full transformation of the sample, and how these different techniques respond to the actual nature of the sample, which is going to be different every time. So helium is non-reactive, right? Well, this is another active area of research. People have synthesized several compounds of xenon, and also here in this sample, in this example of helium as well. Helium is not in this compound of sodium-2 helium. It's not just simply trapped in the cavities, which you could think that actually happen in high pressure. Sometimes you don't even want, but hydrogen helium will penetrate your lattices and become trapped in the interstitials sites. These people, through calculations and then confirmed by X-ray diffraction, they show that actually helium is bonded. This compound, high pressure compound, is also an electride, and what that is that high pressure will force, has such a profound effect on your valence electrons, on your orbital shapes, etc., that is forcing electrons to move basically out, away from atoms, and form a sort of anion without a nucleus in these sites, something that behaves as if it were an anion. It performs bonds and so forth. So that's also quite impressive. Why would an electron not be always around a nucleus, right? And while I'm presenting these, science breakthrough, I would like you to look also at the diffraction patterns, and you can make up for yourself whether or not these patterns, which are still high quality, good results, if they look exactly like what you have practice on, if they look ideal. Another very recent, very impressive result is about lithium. So again, an element, the lightest of metals, is as simple as it can get. We should know everything about elements, you think. And this group shows so many impressive results already at very low pressures. You see these plots end up roughly 10 GPa. These are pressures that we have been, the high pressure community has been able to reach for a very long time. Of course, this is low temperature as well. So this group shows that the two lithium isotopes behaves experimentally in very different ways. So the quantum effect of nucleus has enough energy really to compete with the difference in energy of different crystal structures. Hence, you have a change in the kind of crystal structures you get for these light element, different isotopes structures. And another very intriguing aspect of this work is that by using different PT pads that include pressure, of course, they claim that the ambient pressure, low temperature phase, so the ground state of lithium, the phase is actually different. The one is being accepted for the longest time. They use, of course, experimentally, this is very difficult. You want to have as many different observations as you can. And in most of these studies, you also need first principles and calculations to model and predict your structures. So they did a comparison of total energies, but they did also molecular dynamic simulations, and they actually showed that the phase that was supposed to be 9R is the ground state phase of lithium is actually most likely a martensitic-like crystal structure that they found with molecular dynamic simulations, and then they used to reinterpret neutron diffraction data, and they claim that's a better fit. This is a paper last year, one of the first papers out of the dynamic compression sector, and again, is an element. Here is a schematic of the experiment. So you have a projectile, your sample, your windows. You have other probing techniques that would tell you what velocities are and hence pressures. And you have a detector. So your beam needs to go through these materials and look at the time scales of these diffraction patterns. So 99 nanoseconds, 200, and 600. So these are time-resolved diffraction patterns during a shock. That's actually really impressive. They studied both the powders and the single crystals for this material. With the powders, they could see for the first time for sure what is the high pressure phases, these conditions that was obtained. With the single crystal data, they don't look like the single crystal data that you can collect in your home laboratories, right? 500 peaks aren't these, very sharp peaks, etc. But they are extremely significant, and they use this data the scope of this work is really to look at how deformation happens, whether, first of all, the question will be, if you shock a single crystal, what do you obtain in terms of texture? Do you obtain another single crystal? That would happen to be the case. How does the transformation occur? What is the orientation of the crystal before and after shock? There's another oxide being proposed. You will see that this is particularly interesting to me. This is an iron peroxide. I don't think you heard about this compound before. This was synthesized around 100 GPa and might have important consequence for deep Earth and deep planetary interiors behavior, especially of these of light elements, including oxygen, hydrogen. And again, the diffraction patterns, you see both the image and the pattern, they probably don't look like what you have exercised on. This is an example of also novel chemistry. This group managed to synthesize two hydrogen-rich sodium compounds. They have used theory, they've used Raman and X-ray diffraction to propose these new hydrogen-rich compounds. So, of course, it's something that you want to do for any hydrogen storage, for high-energy materials. And again, if you look at the pattern, which for this material and for these conditions is actually a good pattern, still you have possibly two phases, and your crystal structure is not exactly the simplest. So unfortunately, in many of these experiments, you don't get a diffraction pattern and you're sure what that material is. You have chemistry happening, and it's very hard to probe the chemistry of the chemical composition of such a small sample in such environment. So you don't know exactly what the composition of your crystal is, and you have multiphase. So to summarize these challenges of performing experiment at high pressure. So in general, your data quality is going to be affected a lot anytime your experiment is not going to be your beautiful synthesis at home in the laboratory, and then you bring the sample to the APS, you get this beautiful data that I really love. Unfortunately, anytime you're looking at these sort of experiments, these broadening and increasing range of experiment in which you look at processes, you look at sample in real and strange states. So you have access to this sample through small windows. These windows will also interact with your X-ray of neutrons, so they will give their scattering contribution. Your sample, you probably heard from in XAFS talk that your sample should really have that certain thickness, it should be uniform, it should not have holes and all of these. But that's very difficult to obtain at high pressure. And you have a range of grain sizes, and it changes over time. So the problem is that your data analysis would have, so first of all, you have to be aware of it when you design your experiment, when you collect your data, and also your data analysis might not go through smoothly. Your software that you have been learned, that you've been using for great data might not work for this data. That's a frustration of my students. They say, oh, I followed the tutorial, that works for me, but then I don't know how to deal with my own data. They just, it's the second step, I'm lost, and it's just not working the same way because your data quality, broadening, resolution can be very low, even though we keep improving that side as well. And the interpretation is often not unique. You can have so many different structures that fit your diffraction patterns, that's to stay on the simplest of the technique. But again, all this is evolving rapidly, and anyway, you will want to have as many techniques as possible to narrow down your problems. But there are new ways to do science and different techniques available at all time. So this is actually exciting. Every year you would have opportunities that the previous group didn't have, so you will be able to look at a sample in a different way and discover more about it. I cited lithium, for instance, and samples that were studied before so many times. Well, you have new tools and you can look at them better in a different way. So this is just a slide, for instance, of 3 approaches that are in the literature, 3 of the many in the literature on how to do absorption spectroscopy, for instance. So you have, remember the diamond anvil cell, how it shapes. So you have 2 opposing diamonds. You can actually go through the gasket material, so you need to actually have that gasket made of a material that will allow enough photons to go through, so it's usually beryllium. But if you go through that way, it's very difficult anyway to have the right thickness and throughout for the entire size of the beam. In actual geometry, luckily diamond is actually transparent, basically just completely transparent above 10 keV, so you have so many elements that you can probe the edge of. What happens, of course, diamonds diffract. So if you simply put 2 large, let's remind about the ratio. The diamonds are around 2 millimeters each. Your sample is 10 microns. So you have a sample to device ratio that is not very favorable. So in this plot here, you can see how diffraction affects your absorption pattern as you rotate the diamond anvil cell. So you have Bragg peaks coming in diffraction that will take away some of that incident beam or absorbed beam and produce those glitches. So this group, what they did, they say, okay, we collect all these different angles and we propose this algorithm to basically clean out your spectrum and obtain something that is nearly glitches free, the green one in this plot. This other group from Japan, they said, well, let's develop nanocrystalline diamond anvils. So instead of having well-defined bright peaks, you have broadened peaks and, of course, powder-like, so with symmetry. And so you're smearing out this effect a lot. This other group is using polycrystalline lenses to actually change the beam shape and make it more divergent, again diminishing these glitches and their shape and broadening them out. So finally, I have 10 minutes. I will be talking about my experience. So again, I got into high pressure. It was a new word for me. I was used to high resolution data. I do these high pressure experiments. I get 3 broad peaks, and I'm like, oh my goodness, this is $1 billion machine that I'm using, and I don't know what to do with 3 broad peaks. 3 broad peaks of hydrogen at 200 GPa, I learned that's a big thing. If you can tell the difference between two different simple structures that theory is predicting could be competitive, that's a big paper already. So I learned that lesson. But I also still wanted to get as good data as possible because as you improve your tools, you are actually expanding the science you are able to do. So about 10 years ago, I was part of the group that started to do monochromatic single crystal diffraction in diamond anvil cell. So problem one, you have the windows tend to be small. So lucky enough, the same actually scientists that work here that developed that large volume diamond anvil cell also developed these wide opening support diamond anvil cell, so we can start getting enough access. That you can also get by using some semi-transparent materials to support your diamonds as well. And you need to maintain a crystal in best condition as possible. So we go to a great length to try and keep crystals in environments that are as hydrostatic as possible, or we heat them so we release the strain and we recrystallize them. Still, you have a problem of access to the reciprocal space. It's going to be limited, obscured by your diamond anvil cell, and by the technique you're using. In most cases, single crystal, you do a simple rotation along a vertical axis. So these are actual real data, plot of real data. This is far from your ideal maybe hemisphere of peaks that you would want to have. That's good enough for high symmetry structures, but it might not be good enough for every structure. So what can you do about it? Well, one solution can be to have different crystals orientation in the same dark or in different experiments. And then you have to scale and merge your data. You have these parasitic scattering, so these are the bi rings from the metal that is creates a sample chamber. So your peaks are overlapping and you lose them, so you're losing information once again. You have glitches here too. Your incident beam and diffracted beam will be diffracted by diamond, removing, taking away the part of that strong beam. And this is, it's not impossible in theory to deal with it. You can calculate the orientation matrix of your crystals and the diamond. But of course, diamonds also change under pressure. The peak shape will change. It's difficult to deal with. You can rotate your diamond anvil cell and collect the same peak, and so soon enough, peaks will have this effect coming in and out, and so you can average them all, and your average will be more robust than a single measurement. Again, depends on the problem you're chasing. Recently, I was studying, I had to refine beryllium position in an yttrium compound. So of course, I know I need really good data to nail down that problem. Some other problems, you can live with these glitches. There's a little bit of noise in your data, but they can be as high as 20% of intensities, but they're still manageable. The biggest of the problem, and this is going to be applied to several microdiffraction techniques, is that as you rotate crystals that are, especially when they are roughly the same size of the beam, you are in trouble in terms of amount of photons that actually reach your crystal. If the crystal, these are all possibilities for diamond anvil cell experiments, and they sort of, I'm picturing here conditions that come from different crystal sizes, different sphere of confusion of your instrument, right? Your instrument, when you rotate something, it's a large motors that rotate that thing that is just microns big, so it might move around. That's called the sphere of confusion. And you, as a user, might not be able to put exactly your crystal in the beam, and so you're multiplying the sphere of confusion with your beam, and things move away. And of course, it's all dependent on the crystal size. If it is large, you have a simple, just filling the whole sample chamber. You have a simple omega correction with the rotation angle. If it is smaller, you might not be able to have a simple correction. So what can you do? You can have empirical corrections based on the variation of the intensities of peaks that supposedly should have the same intensities, and derive a fit curve through your actual data and correct for it. This is an example where actually that correction worked really well. I probably was really tired. I was not able to. That's the other component of your high pressure experiments. First of all, you have to be able to prepare all your diamonds or whatever other techniques really well, so you actually get to the pressure the right way. And then you need to be able to perform yourself throughout the whatever length of the experiment there's going to be. And with experience, that changes a lot. You learn what are your own systematic errors that you're going to do, and you put post-it in there to make sure you're not doing that mistake over and over. The other way around this problem that I've applied, especially in case of samples in a cryostat. So a cryostat is a larger device, still not very big, but you want to rotate that device with cooling tubes, all sort of pumps attached to it, and you're moving micron-sized crystals in front of it. So you're rotating 60, 70 degrees. Those pipes and stuff will drag your sample around a little bit. So even though the instrument, the motor itself is pretty good, what you're doing is worsening the kind of measurement that you can do. So you can actually collect multiple exposure, rastering basically moving the zero, the reference position of the crystal. So you do an artificial merging. It's as if the beam were to be rectangular at that point. And so by this application, and you can see here how I changed in a year. I managed to go from that peak broadening to that other peak broadening. The first time, still I managed to understand a lot about this material that you wouldn't be able to do with powder diffraction. You see that this is a study of a spin state, and the collapse of the sudden collapse of the volume of the crystal when you're forcing, you're pairing the spins in a non-magnetic state. And with the second data set, the first data set was not refinable. You could not retrieve good information. And with single crystal, good thing is that you actually are confronted with that. You understand you can't refine. With powders, you have to have more judgment in understanding where you have to stop, what you can actually retrieve from those data. And I was able to chase down this deformation extremely well. But I wanted to do something more, especially with synthesis, something more dynamic. So to me, synthesis in the diamond anvil cell was a way to go. This is a picture of HPCAT 1690B station. The diamond anvil cell is that small thing at the center in there. You have all this other equipment around. High pressure beam lines tend to be really busy. And there's a whole optical table on top of it that allows you to deliver two lasers on the two sides of the diamond anvil cell and collect the image of the sample, the glow of the sample being heated while you collect X-ray data at the same time. That's how it looks like when you actually do the sample. You're starting putting more and more power. The sample start coupling. It's literally glow. You collect that glow. It's black body radiation. You feed to your standard, and you calculate temperature. So you see, this isn't exactly putting a sample in the large furnace. You have actually portion of the sample that glow, and the next micron is cold, is ambient temperature or nearly. So you can have temperature gradients that are almost like 1,000 Kelvin through across a few microns. So your sample is going to be really complex. You want to have the minimal strain. You want to have you need to know that your thermal gradients cause some phases to some phase changes, some chemistry, and some chemical gradients. So what do I do with this sort of samples? Well, I use a very small beam, and I collect images, space resolved image. I map out the sample. These are stationary images, and you can just see how you have a rim of fine grain sample. Still, none of this is technically a good powder, a good statistics powder. You go to the mesoscale, and you have single crystals in the middle. So what I do is to try and collect the best data in each spot. So for samples, I might be able to have multi-grain single crystalline powder from the same 20, 30 microns size sample. And by processing and understanding different grains and different conditions across the sample chamber, I can work out the statistics that those problem affecting crystals that I cannot get rid of, well, they will not be the same for each crystal. And when I look at different crystals, I understand what becomes a problematic signal and what is a clean signal. And I was able to collect a pattern such as this one. This is a very clean pattern to my standard. Still has two large grains of the phase I'm looking at. Has the largest spots there. They are diamonds, diffraction peaks. You have the powder of the bi rings of the standards, and you have some other grains in there. Still, I managed to sort out these things and nail down the structure of a new iron oxides. These are, I invite you, if you're interested in these procedures, there's a video publication that I made. Through these technique, I was able to discover the first two iron oxides that are represented here. So right now we're up to probably 6, 7 new iron oxides, but these were the first ones being discovered. And I was able to map out their distribution, because if the chemistry have to make sense, I want to understand really what happened to the sample when I did that heating. So I hope I delivered this idea to you that high pressure is full of discoveries, a very exotic environment, but there's so much to do. There's so many new techniques available, and there's up to you to really design maybe even new techniques and new problems to look at. There's so many large-scale facilities that allows you to do this sort of experiment, and I can only see a future where high pressure have an even larger role. And I'm going to end the talk here with a slide with 4 books that you can read through if you're interested in high pressure.